This visualization represents the Vehixcare API processing a continuous, high-frequency stream of raw vehicle telemetry data in real time. In enterprise.NET development, a persistent paradox exists. Code that compiles perfectly and passes every unit test routinely triggers complete production outages. Under heavy load, the immediate symptoms emerge. Response times spike unpredictably across all endpoints, followed closely by critical memory usage alerts as the infrastructure degrades. This diagram maps a 20-tier, 150-checkpoint code review matrix. It serves as a deterministic framework designed specifically to identify and eliminate these exact failure patterns. We will isolate 3 specific critical priority tiers on this matrix that most frequently compromise .NET applications. Building a resilient .NET 10.0 multi-tenant API requires moving beyond subjective ad hoc code reviews. Production readiness depends on identifying and neutralizing specific failure vectors through a systematic review of the application's architectural layers. The first invisible failure vector involves microscopic async await anti-patterns that induce system-wide thread pool starvation. This model shows ASP.NET Core assigning HTTP requests to a finite thread pool. Using the .result property inside a synchronous controller to call an async service creates a structural deadlock. The original thread blocks, while the background task requires an unblocked thread, resulting in mutual exclusion. In background services, executing tasks via async void creates a different hazard. It completely swallows internal exceptions, causing the application process to crash silently. Attempting to offload CPU-bound web tasks using task.run acts as an accelerant. It pulls additional threads from the pool for internal processing, rapidly depleting the remaining resources. Once thread pool starvation occurs, the entire API comes to a halt. The application becomes completely unresponsive, regardless of the underlying CPU or memory capacity. The Tier 1 matrix checkpoint requires the mandatory propagation of a cancellation token across all boundary layers, allowing the system to abort hung requests and free occupied threads. It also enforces the architectural rule of applying configure-await false within library code. This prevents the unnecessary capture of the synchronization context, directly reducing thread contention. Improper thread yielding turns these microscopic sync over async calls into structural deadlocks that collapse the entire request pipeline. The second point of failure lies in outbound network calls and the exhaustion of ephemeral port limits. A common code pattern wraps a new HTTP client instantiation inside a using statement for every external service integration. This diagram illustrates the TCP/IP lifecycle. When data transmission ends, the gateway node locks into a restricted state marked time wait for exactly 240 seconds. With a limit of 16,384 available ports, high-frequency telemetry requests hit this physical ceiling in under 4 minutes. This triggers a socket exception cascade. The server appears perfectly healthy regarding CPU and memory, but it becomes structurally incapable of opening new outbound connections. The matrix-enforced architectural fix requires the centralized registration of an IH client factory during application startup. By utilizing typed or named clients, the factory internally manages the underlying HTTP message handlers, reusing established connections and entirely bypassing the port limit. External API dependencies also trigger the Tier 12 resilience requirement. Integrating poly retry policies with exponential backoff ensures the system absorbs transient downstream failures without crashing. Implementing a circuit breaker pattern configured to trip at a 0.2 failure ratio instantly isolates degraded downstream services, preventing further resource lockups. High-scale HTTP integration requires managing the underlying connection handlers through strict resource pooling. The final internal threat stems from uncontrolled memory allocation and the cascading penalties of garbage collection. This diagram shows 3 memory tiers. The N+1 query pattern silently scales data retrieval volume by executing separate database calls for every related record. Omitting as-no tracking on read-only endpoints forces the database context to track state changes across thousands of immutable entities, incurring severe Generation 2 memory penalties. The Tier 4 matrix checkpoints mandate the use of array pool. This allows the application to reuse large telemetry buffers without triggering new allocations on the large object heap. In the database layer, enforcing explicit projection definitions restricts query execution to only the exact required fields, eliminating unnecessary memory overhead. Memory exhaustion is an architectural choice. Uncontrolled allocation guarantees fatal latency spikes during system-wide GC pauses. Zooming out from isolated code fixes reveals the macro architecture required to stabilize an application like the Vehixcare API. This structural hierarchy demonstrates the domain infrastructure exception handling boundary, a distinct separation barrier between external infrastructure components and internal domain logic. The absolute rule of this boundary is isolation. Raw infrastructure faults, such as MongoDB timeouts or dropped TCP sockets, must never bleed directly into the domain layer. Implementing the result pattern ensures the boundary intercepts these raw exceptions, translating them into predictable, standardized response structures. Threat starvation, socket exhaustion, and GC pauses operate under distinct mechanisms, but they are all predictable boundary violations. By applying the 150 checkpoints within the matrix, the Vehixcare implementation targets the core failure vectors responsible for telemetry ingestion collapses. Senior engineering requires abandoning reactive bug fixing in favor of proactive, matrix-driven architectural compliance. Production-grade resilience is achieved when an application is structurally architected to isolate, contain, and survive its own inevitable infrastructure failures.